This is section 12.3, Geometric Sequences and Series. Last time we talked about a special type of sequence which produces a special series, the arithmetic sequence and arithmetic series. And today we're going to talk about the geometric sequences and series. So, first of all, let's look at one that's geometric. See if you can figure out the pattern. So we've got 2, 6, 18, 54, 162, etc. What's the pattern? What's going on here? Well, if you said, or were thinking, multiplication by 3 to produce the next term of the sequence, you're absolutely right. And here's another one. What's its pattern? Now you may be tempted to think that it's division by 2, which is technically correct, but I'd like for you to think of it as multiplication. So multiply 8 by what number to get 4? It's 1/2. And the reason I want you to think about multiplication is because the thing that makes a sequence or series geometric is the fact that you're multiplying by a constant each time to get the next member of the sequence. And so arithmetic, you're adding a constant to produce the sequence. This is multiplying by a constant to produce a sequence. Now, the number we're multiplying by is called the common ratio. And so the common ratio for the first one is 3. And the common ratio for the second one is 1/2. And just a word about how it became a common ratio. Take any pair of numbers that are adjacent to each other in this sequence and take the one that's after and divide it by the one that's before. And it doesn't matter which pair you pick, you'll always get the common ratio. So for the first sequence, doing those division problems gave me 3 no matter what. And here, like 2 divided by 4, or even 1/4 divided by 1/2, the answer is always 1/2. So that's the ratio that's formed of 2 adjacent members of the sequence. The latter one minus the earlier, not minus, excuse me, divided by the earlier one gives you the common ratio. Okay, so that's how we can understand what it is for a sequence to be called geometric. So here's another one. 1, 2. This is actually a famous problem from the ancients. They actually thought about this. But to put it in today's language, let's say that I'm going to offer you a job. And after your first day of work, I'm going to give you 1 cent. And after the second day, I'm going to give you 2 cents. And for the third day's work, I'll give you 4 cents, etc. Is this a job you would take? All right, well, you may notice that this one is geometric. Pretty quickly. And that its common ratio is 2. Because you're always doubling the last answer to get the next one. So, if that's true, let's use this pattern to see if we can develop something that's true about all geometric sequences, kind of like what we did with the arithmetic ones earlier. So what we're going to do is think about what we had to do to get the answers for this. So the first term is 1. You get the second term by multiplying that answer by 2. You're going to get the next answer by multiplying that answer by another 2. And then you're going to take the previous answer, 1 times 2 times 2, and multiply it by yet another 2, etc. And so how is it that we can get repeated multiplication going on here? In other words, I'm trying to find a pattern for a sub n. It's going to be 1 times some number of 2's, dot, 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 times 2. And we need an expression for that. So if you'll notice, every single time it is the first term multiplied by some number of the common ratio. And let's go to a sub 4. That's 1 times 2 times 2 times 2. Another way to write that is 2 cubed. The one before that is 1 times 2 squared. The one before that, 1 times 2 to the first. And actually the very first one is even 1 times 2 to the 0, following that pattern backwards. And just like what we did for arithmetic sequences, what is that power of 2, like looking at the a sub 4 answer, where the power of 2 is 3, how does that 3 relate to the n value of 4? Well, of course, it's 1 less than that. So this is going to be 1 times 2 to the n minus 1, because we're going to multiply n minus 1 of the 2's together. And so in a more general sense, the nth term of a geometric series, or sequence I should say, we're not adding them yet, so let's call this a geometric sequence to be consistent, will always be the a sub n, the nth term, will always be the first term times the common ratio raised to the n minus 1. And that's a formula that you need to commit to memory. All right, so now that we have that formula, let's do some problems so that we can kind of get our feet wet with this nth term of a geometric sequence formula that we just came up with. So let me ask a question. And this, if you read the earlier sheets, this question was posed with this sequence of 1 penny for the first day, 2 pennies for the second day, etc. The first question I'd like to ask is, how much will be earned on day 20 if daily wages follow that sequence? So we've already established that the common ratio is 2, and of course the first term is 1. So for this particular sequence, a sub n will be a sub 1, which is 1, times r, which is 2, to the n minus 1. And of course, 1 times anything is just itself. So this is the simplified version of the a sub n formula for this sequence. So the question is, how much will be earned on day 20? Well, that'll be the 20th term of this sequence. So that's going to be 2 to the 20 minus 1, which is 19. And the answer to that is 524,288. And what were the units for this? It was in pennies, right? Cents. So it'll be that many cents. And if we divide that by 100, that's $5,242.88 is what you earn on day 20 for 1 day of work. Well, that's quite a tidy sum. We'll keep working on that and come back to that problem later. So let's look at this one. we're given a geometric sequence for negative 12, 36, negative 108. We're told that it's geometric. And we probably should make note of a couple of different numbers that are required to be known in our formula. That is, what is the first term? That's easy. It's just 4. And what is the common ratio? If you want to think, what would I multiply 4 by to get negative 12? That works. Or you can also say, divide any term like 36 by the one before it, negative 12. 36 divided by negative 12 is negative 3, the same answer. The question here is to find a sub n for this sequence and find a sub 5. Okay, so a sub n, using that memorized formula, is a sub 1, which is 4, times negative 3. Make sure you put that in parentheses when it's a negative number. It's really important. To the n minus 1. To the n minus 1. Okay, so that's the formula a sub n. So a sub 5, using the formula, is 4 times negative 3. 5 minus 1 is 4. So negative 3 to the 4th is positive 81 times 4 is 324. Now we could have gotten the fifth term by following the pattern, taking negative 108 times r, which is negative 3, and gotten the same answer. And of course that's not really the point on this one, because I could have asked you for the 15th term or the 50th term, and you certainly would not want to find all of the ones in between to answer that question. So if it's really close, the question is asking for one that's really close, you can just keep with a pattern if you want to. But of course at some point you're not going to want to do all that work. And so it's probably good that you know both ways for a sub 5 here. All right, next one. Another example. We're supposed to find r and a sub 1 for the geometric sequence. So we know it's geometric. And now it's important you pay attention to that, because they could slip in an arithmetic problem. So be very aware that you know what you're doing. They tell us that the third term, a sub 3, is 20. And they tell us also that the sixth term, a sub 6, is 160. Well, the thing we know is true is that a sub n is equal to a sub 1, one of the things we're supposed to be finding, times r, which is another thing we're supposed to be finding, to the n minus 1. Given these two pieces of information, we know that the answer is 20 when n is 3. So I'm going to substitute 3 in for n. 3 minus 1 is 2. We also know that the answer is 160 when a sub 1, which we still don't know, times r, which we still don't know, to the n minus 1. And for the answer to be 160, n is 6. 6 minus 1 makes that 5. Now, what we can do to find this is to solve this, which is basically a system of equations. Two equations next to each other there, for which we have two equations with two unknowns. So probably the smartest way to solve this is by substitution. Take one of the equations and solve for a sub 1. It does not matter which one. So I'm going to take the first one and solve it for a sub 1 by dividing both sides by r squared. Then I'm going to take that and into the other equation and replace a sub 1 by substitution with something that's equal to 20 divided by r squared. That equation is solely in terms of r, which means we should be able to solve it for r. So first, I guess we should do some simplification. R to the fifth divided by r squared leaves r cubed. Then dividing both sides by 20 leaves 8 to be equal to r cubed. And then taking the cube root of both sides, the principal answer for that is 2. We wouldn't be interested in the other two answers because they're complex non-real solutions, and we're generally looking for only the ones that are real numbers. All right, anyhow, so r would be 2. And so we can then take that information back into the equation where we solved for a sub 1 and substitute for r with 2 and solve for a sub 1 now. So a sub 1 ends up being 20 divided by 4, which is 5. So if we look at the original question, we were supposed to find r, which we have done. We were supposed to find a sub 1, which we have done, and that completes that problem. All right. So let's see what else we have here. Turning to the next page. Modeling accuracy of professional golfers. At a distance of 3 feet, professional golfers make about 95% of their putts. For each additional foot of distance, this percentage is 0.9 times the previous percentage. A. Write a formula that gives the percentage of putts pros make at distance n, where n equals 1 corresponds to a 3-foot putt. Okay, let's see. This is actually a geometric sequence because we're going to be multiplying 0.9 times the previous percentage. That's what puts us into the geometric sequence mode. So a sub 1 is going to be the percentage of putts made at 3 feet. Okay, so that is 95%. And we're going to write percent as a whole number. So instead of 0.95 here, we're going to make it 95 to stand for 95%. And R is 0.9 because that's what we're going to multiply each time by. Okay, so with that information and knowing that it's geometric, that says that a sub n will be a sub 1 times 0.9 raised to the n minus 1. Okay, so that's the formula that gives the percentage of putts that pros make at distance n. B, it says estimate the percentage of putts made at 20 feet. That is when n is 18. Okay, so when n is 18, that means a sub 18 will be, according to the formula we derived in part A, 95 times 0.9 to the 18 minus 1, which is 17. And then using our calculator, we can approximate that, and that ends up being about 15.8. So at a distance of 20 feet, about 15.8% of putts are made. By professional golfers. All right. So, now, if we want to know the sum of the first n terms of a geometric series, they call it a sequence, but of course we know it's a series because we're adding the terms. But anyway, the first n terms, we're adding them up. And of course this is for geometric. There is a formula like this for arithmetic ones, as we saw in the last one. And S sub n, the nth partial sum, is the other name for that. Let me write that down again. The nth partial sum, S sub n, capital S sub n. The nth partial sum is the first term times 1 minus r to the nth. Make sure you realize that that n is on the r, not on the binomial. It's not the quantity 1 minus r raised to the nth. It's 1 minus the nth power of r. So be very careful you get that n in the right place. Divided by 1 minus r. And of course, since we don't want to divide by 0, r can't be 1. So another question from the beginning of this was, if you start with 1 cent for a first day of work and 2 cents for the second day of work and keep doubling for each subsequent day of working, one of the questions we could ask is, how much will you have earned altogether if you work 20 days? So in that sequence, I'll remind you that the first term was 1 cent and our multiplier was 2, so r is 2. And so the total amount of money earned after 20 days of work under those conditions is 1, which is 1 penny, so a sub 1, times 1 minus r, which is 2, to the 20th. Please notice that this uses n, not n minus 1. You've got to be very careful that you don't accidentally conflate these different formulas and mix them up with each other. Divided by 1 minus r, which is 2. And when you do that in your calculator, you get 1,048,575. And what are the units of that? That's cents. And then, so how much is that in dollars? $10,485.75. It's not bad. Work 20 days and have $10,000. That's a job you could probably talk me into. Although the first few days is not much money, you end up raking in the big bucks before long. All right, so let's look at series for sigma with I going from 1 to 6 of 2 times 3 to the I. So let's expand this one. 2 times 3 to the first plus 2 times 3, now put in 2, plus 2 times 3 third, raise to the third, plus 2 times 3 to the fourth. And of course we need to keep an eye on when we're supposed to stop. That's after we substituted in 6 for I. That's our very last one. So that's what that series represents. So, they want us to do is find this, and of course you can recognize the fact that this is geometric. The first term would simplify to be 2 times 3 to the first is 6. And R, of course, you're multiplying by 3 to go from term to term. So S sub 6, which we could do by finishing the problem above, doing all that arithmetic and getting the sum, but this is to practice our formula, is S sub 6 is A sub 1, which is 6, times 1 minus R, which is 3, to the nth, divided by 1 minus R. And you do that arithmetic, and you should get 2,184. You would get the same answer if you did all of the arithmetic in the line above. And when your n is small, expanding it and doing the arithmetic seems like a pretty good plan. But if that had been from I equals 1 to 67, you would not want to write those terms down, those 67 terms, and then do all that arithmetic. You would want a formula like this one. Okay? So, an infinite geometric series is, of course, one that keeps on going. So if we start with this geometric sequence, this is similar to one that I brought up early on in this lesson. This geometric sequence, let's look at the partial sums. The first partial sum is the first term. The second partial sum is the sum of the first 2 terms. So far this hasn't been that hard. The third partial sum is the sum of the first 3 terms. See, that's 7 halves. And the fourth partial sum of the first 4 terms. Is 15/4, etc. So, if we were to continue this, what we would be wondering is, does this converge on a value? Does the sequence of partial sums converge toward a particular value or not? So we're looking at this sequence of partial sums, and we want to know, does that head toward something or not? If you look at the calculator table that was generated, you've got more answers, and they're in their decimal form, which is fine. And as n gets bigger and bigger, does u sub n, which is the declaration of the sequence of partial sums, does that appear to you to be getting closer and closer to any particular number? Sometimes it takes seeing up where n is really big, like maybe 25 or 50 or something, before you settle on what you think it's headed toward. But as they say there, over to the right, it does appear that you're getting closer and closer and closer to 4. So if we kept going, we would assume that S, which they in this book call S sub infinity, we assume that that's 4. I'm going to write approximately equal to 4 because we're not absolutely certain yet that that's actually true. But for right now, let's just say that evidence of the graphing calculator screen is pretty convincing that it's 4. Okay, so let's look at another one. 1 plus 1/3 plus 1/9 plus 1/27 plus ... Of course, this is geometric, where a sub 1 is 1 and r is 1/3. And so s sub n for this one would be s sub 1, which is 1, times 1 minus 1/3 to the nth, all divided by 1 minus 1/3. And if we were to think about what would happen if n approached infinity, which is something we can do with a limit, we can say the limiting value, the value that s sub n is approaching as n approaches infinity, is what this means. Then by substitution, I can replace s sub n with 1 minus 1/3 to the nth divided by 2/3. I just did a little bit of the arithmetic. 1 times anything is itself, and of course 1 minus 1/3 is 2/3. And as you multiply a fraction like 1/3 by itself over and over and over, what's happening to that value? Like, what's 1/3 to the 15th? What's 1/3 to the 100th? What's 1/3 to the 200th? And if you do that in your calculator and made n bigger and bigger, you'll see that that 1/3 to the nth is approaching 0. So we're left with 1 over 2/3. To divide fractions, you multiply the numerator by the reciprocal of the denominator. And so that's 3/2. In fact, as it turns out, by the way, that's called S, the sum of that convergent geometric series. So S is the sum of all those terms. As it turns out, that happens for many of these problems. Let's go back and look at the one where we assumed it was 4 because of the evidence in front of us. If this one converges, its sum S will be the limit as n approaches infinity of S sub n. So the S sub n formula in this one is, first term is 2 times 1 minus r, which was 1/2, raised to the nth, all over 1 minus 1/2. 1/2 repeatedly multiplied by itself is going to head towards 0, like 1/3 did as well. And if you finish the arithmetic on this one, you actually do get 4. So what's happening is, because it's a fraction for r, if you multiply a fraction by itself over and over and over again, the answer just gets closer and closer to 0. And so what that means is that there's a formula for the sum of a convergent series. The sum of a convergent geometric series S is equal to a sub 1 times 1 minus a fractional r raised to the nth over 1 minus r, every single time r is a fraction, repeatedly multiplying it by itself means that that r to the nth term will go towards 0, leaving a sub 1 times 1 minus 0 over 1 minus r, which simplifies to be a sub 1 over 1 minus r. Now, that only works when the geometric series converges, and that's going to happen only if the absolute value of r is less than 1. Okay? That's only going to happen in certain circumstances. And in order for that to happen, r has to be a value that, when you take the absolute value of it, it's less than 1. By the way, geometric series diverges. The geometric series diverges if the absolute value of r is greater than or equal to 1. Okay, so that's what that has to be. All right, so that's another formula. S equals a sub 1 over r minus 1, first and last thing in that row up there, when the absolute value of r is less than 1. That's a formula you need to commit to memory as well. Okay, let's do an example or two. We're supposed to find this infinite sum, starting with I equals 1 and going to infinity. We have negative 3/4 times negative 1/2 to the I minus 1. So the first term, when I is 1, 1 minus 1 is 0, negative 1/2 to the 0 is 1, 1 times negative 3/4 is negative 3/4, plus, now put in 2 for I, 2 minus 1 is 1, negative 1/2 to the first is negative 1/2, negative 1/2 times negative 3/4 is positive 3/8, etc. This one is geometric. I know I didn't find very many terms, but this takes the form of a geometric one. Whenever you see sigma of a constant times r to the n minus 1, or n, depending on what you start n as, then that's always going to be geometric. Okay, so anything that looks like that behind sigma, a constant times a constant raised to n or n minus 1, will be geometric. So using that, I can say this is geometric pretty fast. And I can say, well, the first term is negative 3/4, and r is negative 1/2. Since the absolute value of this particular r is less than 1, because of course the absolute value of negative 1/2 is 1/2, and that is smaller than 1, then we know the geometric series converges. And since it converges, we know what it converges to. It converges to S equals a sub 1 divided by 1 minus r. And you do that arithmetic, and you get negative 1/2. Okay. All right. I'm going to end this session with that example and start a new one for the rest of the notes on this section.